Okay, and welcome to the proper start of week one of stat modeling. So where we're heading is we're going to take linear regression and we're going to improve it. We're going to start saying, well, how do we choose the best linear regression model? What do we do when, for example, our response variable is a success or a failure, or stuff like that. So we're going to slowly build back. Before we do that, I'm going to do a bit of a recap. Over the first couple of weeks, we're going to recap linear regression and make sure we've got on a solid basis. And one, it's always nice to recap, and two, we're going to make it a bit more mathematical. So, before we do that, before we start with our linear regression, I'm just going to recap some notation. So, first of all, we've done this before, but now we're getting to third year, we're going to have to be a bit more careful. I'm going to represent random variables. So this is something that takes a number that has a probability associated with it. When it's a random variable, I'm going to use an uppercase letter. For example, here I've got an uppercase Y. When I actually observe a value, that is I go, actually Y equals 5, when I want to represent that observed value, we use lowercase. And the thing to remember, if it's lowercase, we know the value. If it's uppercase, we don't know it yet. So when it's uppercase, it's still have a lot of probability. We haven't sort of locked it down, and when it's lowercase, we've locked it down. So we're going to have a collection of these random variables together, which we will call random vectors, and occasionally have a big collection in a matrix, which we'll call a random matrix. And we're going to consider in this course, to make it simple for ourselves, we're going to consider variables where they have an expected value or mean and a variance, so they exist. So here's definition 1.1. Imagine I have n random variables, y1 up to yn, and I put them in an n by 1 vector, where the first element is y1, then y2, all the way to yn. I can indicate that this is a random variable by, first of all, calling it y, and notice it's bold. The bold tells me it's a vector. So I've got this stack of random variables. Now we said that they can have an expected value, so I can have a vector that would represent their expected value. And by default in this course, we'll call that eta. That's that funny looking n. And let's see if, yep, there we are. There's my funny looking n. And eta is going to be defined as the expected value of y. So the first element now, instead of being y1, is the expected value of y1, then y2, all the way up to yn. So we could define this as eta1 is the expected value of the random variable y1. If we're going to have means, we can also have variances. So we could have a variance of this y, and this is going to be, because we had our length of our vector was n times 1, this is going to be an n by n matrix. And the most common thing is we defaultly call this sigma. So this is the capital sigma. You've seen the small case sigma, there's just one here. And what sigma is, it's a big matrix where the ith row j column element will be the covariance of yi and yj. So if I, sort of like you go down the row, which gives you the first random variable, you go to the column, which gives you the second, and that will give you the covariance. What happens when I equals j? Well, remember, the covariance of yi and yi is the variance of I. So along the diagonal of our matrix, we get all the variance terms of our random variables. Okay? So that's the way we set it up. Occasionally we'll have a random matrix, so now instead of just a single column, imagine lots and lots of columns. I've got this curly y to denote this, and basically the ith jth entry in my matrix will be the random variable yij. And if I had the expected value of that, now I'd have a matrix of the same size, where each element would be the expected value of the ith jth random variable. Let's now take our linear transformations you've seen before. You saw them in probability and stats with me, you've seen them a couple of times, but now put them in the matrix form. So we've got a random variable y, so it's a random vector, so we'll assume it's like n long. And then we've got the expected value of this, which we denote by eta, and the variance we denote by sigma, so it's all set up. And now what I'm going to do is I'm going to consider two things. I'm going to consider a matrix A, which has n rows and n columns, and it's just numbers, it's constants. We've done this before, we did sort of y equals ax plus b, where we had a and b were constants and x and y were random variables in that case. All we've done now is we put it in the vector case. So now instead of my a just being a number, now it's a big matrix. And it's designed that it's m times n, so I can pre-multiply it by my random vector y. B is a vector, it's an n by 1 vector, and again these are constants. So A and B are not random, they're constants. Then, if I wanted the expected value of this matrix A times my random vector y plus a random vector B, then I just write that as A eta plus B. Now, it might look complicated, but that is just exactly the same. If I'd given you and said, y equals ax plus b, and I said, what's the expected value of y? You would have went, oh, John, it's just, the expected value of x plus b. This is just the vector matrix form. What about the variance? Well, the variance before, if you were doing this, would have been, if it was just in the scalar case, would have been a squared y. So we need almost the matrix equivalent of that. And all it is it's A sigma A transpose. And remember, by transpose, all I've done is I've flipped the matrix around. So whatever is in the element, say 1, 2, would now be the element 2, 1. You sort of rotate it across. All nice. If we had a random matrix, so we've gone another layer up, and A is a fixed matrix, then the expected value of AY equals A expected value of Y. I'm not going to give you the variance equivalent of that, it's a bit more complicated. Also, we will occasionally have, at the moment, we've just got a random vector. We know its mean, we know its variance. We've done a linear transform of that, but we've had no discussion at all of what the distribution is. One of the most common distributions we're going to look at, especially in linear regression, is the normal distribution. So we've got this notation. I've got a random vector y, so assume it's an n times 1 vector of random variables. And we're going to say it's nr. Actually, so I should have said it's an r times 1. Changed my notation right in the middle because I thought in that first lecture, why not make it complicated for you? Yeah. Remember all the people who did the course with me before and went, oh, Jono, that's right, you just make stuff up as he goes along. Yep, still doing that. But anyway, we're going to say it's normal of dimension r. It's going to have a mu, which is going to be, it's basically mu is the eta for the normal distribution, so it's going to be a column of expected values. And we're going to have a variance covariance of sigma. In this case, we'll say this is an r-dimensional random vector y, so it will be an r by 1 random vector. It has a multivariate normal distribution with a mean vector of mu and a variance matrix of sigma. Good. So now we can take the distribution results we had before with the linear transformation, and we know that the nice thing about the normal is if you take linear transformations of normal, you still have something normal. So we've got our random vector y. It's normally distributed with a mean of mu and a variance covariance of sigma. We've got a matrix of constants and a vector of constants. Then AY plus B is going to be normally distributed with a mean of A mu plus B. So I use that lemma from before. A sigma A transpose. Nice and easy. And if Y is the same and we just have a nice thick vector here of A and we go A transpose Y, then that's going to be normally distributed. It's now got no subscript because it's a single scalar, because this is a single number. And it'll be A transpose mu, A transpose sigma A. Cool. We'll be using these lemmas again and again, so it's worthwhile just marking these and knowing them. So when we get to exams and stuff like that, you can look them up really quickly. So that's some notation, some setup. Next time we will start looking at multiple regression. See you next time.